and welcome back to IAC 101, a video series created by the Center for Advanced Energy Systems at Rutgers University. This video series is based on the experiences gained through the U.S. Department of Energy's Industrial Assessment Center program. I'm Dr. Mike Muller, Professor of Mechanical Engineering at Rutgers University, and in this series I'll be breaking down the various energy systems that you may encounter at a typical manufacturing plant. In episode 1, we looked at the supply side of industrial compressed air systems, including types of compressors, compressor room hardware, control schemes, and ways to maximize system efficiency. Today, we are going to focus on compressed air distribution and the various appropriate and inappropriate end uses that you may see in a manufacturing plant. When dealing with compressed air economics, it's important to understand not only the upfront cost of buying a compressor, but how much it costs to operate it over its lifetime. This chart shows the typical life cycle cost of an air compressor, and as you can see, most of the cost comes from operation rather than the initial investment of purchasing the compressor. In fact, it typically only takes 12 months for the operating costs to exceed the initial purchase cost. So if your plant is in need of a new compressor, don't get too hung up on the initial cost up front. Instead, focus on managing air use. Now, if you're somewhat new to what we use compressed air for and why everybody talks so much about it, you'll find that compressed air is often used to actuate tools and machinery using a large variety of actuators. Compressed air is used to move, sort, collect, push parts during the manufacturing process. A large variety of compressed air actuators, like the ones you see here, exist because they are designed specifically for each process, depending on the length of motion, the type of motion, is there any rotation needed. For example, a single handling and packaging line may call for 15 to 20 different types of actuators just to get the job done. Another big end use of compressed air is hand tools. Hand tools include grinders and nailers, wrenches, sanders, or any of the other devices shown here. Just like actuators, there is a great variety of hand tools to cover many different applications. Air knives are used to process equipment to separate things. We see spot coolers use vortex tubes to get a cold jet of air. And it's not uncommon to see compressed air being squirted into liquids for mixing or aeration. Sandblasting is the use of compressed air to smooth rough materials. Small round shots of hard metal are used to smash into material and smooth it, and are carried by compressed air. Sometimes sandblasting is used in preparation for painting. And the painting process itself normally uses compressed air to atomize paint into small droplets for an even application. Plastic products like milk jugs are formed using compressed air to push material into a mold, and this is called blow mold extrusion. So for the processes I just mentioned, the compressed air needs are going to be large and continuous. This chart shows the average flow used by compressed air hand tools measured in cubic feet per minute, or CFM. So how do you determine the right size compressor to put in your plant? You may be thinking you could just tally up all the actuators and hand tools that are used in the plant and multiply each one by its rated compressed air usage and hours of operation. Well, you could do this, but it'd take you a long time and it's not always very accurate. Another way to determine compressed air usage would be to set up flow meters at various points throughout the plant. There you could physically measure how much air is being used. This gives you great insight into the plant's actual compressed air usage over time. But this is not done as often as you might think. Flow meters cost money, and air use will change anytime you have even a small change to your process. The bottom line is, when a plant is designed, the size of the compressor is often guessed at by management. This leaves the possibility of a greatly oversized system, and is the reason that compressed air usage is one of the first things that a good energy manager is going to look at. Now we're going to look at two scenarios where we use measured trend data from an operating plant to assess its compressed air system. In the first plot, the green line shows the dew point, the orange line shows the air pressure, and the blue line shows the flow rate. If we look at the blue line first, we see that the flow rate varies dramatically over time, with spikes as large as a factor of 2. However, if you look at the orange line, you'll see that even though you have these spikes in the flow rate, it has almost no impact on the compressed air pressure that is being delivered. This is an example of a good case scenario: steady efficiency and pressure with varying load. You have to be careful, however, because if you have a greatly oversized air compressor, you'll see the same kind of data, and so you have to be wary of that. The next graph shows a bad case scenario. In this case, we're looking at the line pressure delivered by a compressed air system over time. We can see that while the system is trying to give us a pressure of about 105 pounds, for the majority of the day, from 7 a.m. to 7 p.m., we're unable to keep the pressure at that level. This tells us two things. First, that you're operating the pressure of your system too high. We know this because the system is still working when you have lower pressures of around 85 pounds per square inch. Secondly, it tells us that you're trying to use the compressed air system itself to store extra air. In this case, we would recommend an increase in compressed air capacity and the addition of some storage tanks or receivers to level things out. So how do we reduce the amount of compressed air we use? Let's start by looking at a breakdown of compressed air end-use estimates. You might be surprised to learn that only about 45% of compressed air produced is used for production or for the manufacturing process itself. And this number normally cannot be changed very much unless the process itself is changed. But as you can see, there is the potential to cut down on the other 55% of usage, which is lost to leaks, inappropriate uses, and artificial demand. Leaks are small holes and gaps in air lines or fittings that allow air to escape to the atmosphere before it is used. And although each individual leak may be small, air leaks make up 20 to 30% of compressed air usage. Now, an inappropriate use is when compressed air is used in ways when another device, such as a fan or blower, may do the job more efficiently. This makes up about 10% of compressed air usage. And the remaining 15% goes to artificial demand, which is a little hard to understand, so I'll give you an example. Say, like in the previous graph, you're not getting enough compressed air in your system. You only need 85 pounds per square inch, but the system is set to 100 pounds. Well, guess what's going to happen now? All of your leaks and inappropriate uses are going to have extra large flow rates. Artificial demand is the extra loss associated with having pressure that is higher than necessary. The easiest of these end-use losses to attack is inappropriate use. Here are a list of some of the most common ones. Personal cooling. When a worker says, "Hey, I want to blow air on myself because I'm hot." Then there's using compressed air for cleaning and drying. This is fine for the occasional cleaning of a workbench, but in many cases we see continuous blowing to keep dust off of a product. In those cases, a blower using an electric motor would be a much cheaper alternative. One benefit of using compressed air rather than electricity to run a motor is there are not electrical hazards. But it's unnecessary to use air motors for non-hazardous scenarios like mixers when you could be using cheaper electric motors. The last example of inappropriate use is abandoned and idle equipment. Compressed air will keep being used by those systems unless they're valved off. Next is the biggest headache anybody has with compressed air: leaks. Air under pressure tends to leak, so constant vigilance is needed to find and fix leaks. This may seem tedious, but managing leaks can lead to large savings as leaks waste 20 to 30% of generated compressed air. When you're visiting a plant, ask if they have a program to continuously find and fix air leaks. If they don't, tell them that it's a good idea to outsource compressed air system maintenance to a third-party service. Here's something that's obvious but often overlooked when you're talking about air leaks. They don't only affect frequently used equipment. For example, an airline serving a pneumatic tool that's only used periodically, say for only a few seconds to a minute every hour, is just as likely to have leaks as a tool that is constantly in use. And leaks continuously drain your compressed air power. so they'll waste air whether they're being used or not. This is why working on fixing air leaks can really save money. So for example, if you have a 25 horsepower compressor and use a rule of thumb that compressors produce about 4 CFM per horsepower, so if you do a little math, as shown here, you see that a 1 CFM leak over 1 year of operation can cost a plant $80. But as it turns out, it's very difficult to quantify the effects of any single leak. This is because the pressure on the inside of the line is typically 80 to 100 pounds, whereas the pressure on the outside is atmospheric, or 14.7 pounds per square inch. This creates a pressure ratio big enough that the flow going through any leak is going to have what we call choked flow, and have a Mach number of exactly 1. The more you increase the size of the hole, the higher the flow rate through the leak. So you can estimate the losses for an air leak by guessing the size of the hole and the airflow through it. However, keep in mind this is not a perfectly accurate technique. It's also challenging to locate where leaks are. One common way of finding leaks is to spray soapy water on airline, links, fittings, and other valves to see if bubbles come out. The creation of soap bubbles indicates a leak. A second, higher tech way is an ultrasonic air leak detector. These devices work based on the principle that ultrasonic noise decays very rapidly away from its source. Therefore, if you hear a large amount of ultrasonic noise on a compressed airline, there is most likely a leak present. These devices are sold at low prices, so it's a good idea to have one around to play with, but they don't always work well in loud manufacturing plants. However, if you're in a warehouse or another quiet location, this method is very effective. Okay, so with a relative inability to measure individual leaks, most plants will try to implement some sort of system-wide leak measure. The best way to do this would be to put flow meters at several points throughout the compressed air system so that you can isolate certain lines. By this I mean turning off known compressed air use within a small section of the plant and seeing if the flow rate goes down to 0. Not really 0. Realistically, about 10% of full load flow is about the best you can achieve. If this doesn't happen, you definitely have some work you can do on fixing compressed air leaks. You can also take advantage of times when the plant is in shutdown mode. Line pressure will drop over time due to leaks in the system, so even with the plant shut down, the compressor will continue to cycle on and off to maintain the pressure set point. This average cycle time gives you a good measure of the overall system's health. This graph shows the results of a company that did a top-notch job in eliminating their air leaks. The left-hand part of the graph shows system pressure over time before implementing an aggressive air leak reduction program, and the right-hand side shows system pressure after that. The first thing you see is that the non-production shutdown level goes down to about 10% of the system's maximum pressure. So this program is working very well. And if you think you can do better than 10% of the max, you're a little nuts. 10% is about as good as it gets. Additionally, when the system fires up and goes to a higher pressure, you see that there's only about a 12% reduction in overall flow rates, which turns into direct dollar savings because the compressor does not have to work as hard to maintain flow. So where are the best places to look for air leaks? This graph breaks down the places where leaks occur. A lot occur at places you might suspect, like joints, valves, and quick connects. Then there's this crazy acronym FRL, which accounts for about 46% of all leaks. What the heck is this? Okay, so here's an FRL. FRL stands for Filter Regulator Lubricator. FRLs help to ensure that the system has enough oil and that you're draining things like dirt out of the line. Also that you're maintaining the pressure that you need. These devices can be found all over the plant, so when you start looking for leaks, start by checking the FRLs to make sure they're all tight and secure. You can also get fancy and start installing smart FRL devices. These FRLs track flow pressure and the status of the filters and report this data to the cloud. I've not seen a lot of these devices in place yet, but clearly this is the direction we are heading in as the Internet of Things becomes more of the norm. Another common device you're going to see on the end-use side of a compressed air system is a surge tank, also called a receiver tank. The primary purpose of a receiver tank is to be a buffer or a smoother. Receivers store compressed air to help keep the pressure constant at times of peak demand. Without a receiver tank, cyclic changes in pressure can alter the performance of actuators and other tools. These tanks are upright and big, and usually many of them are used in series to produce a variety of pressure levels. This picture shows 6 receiver tanks of various sizes. Receiver tanks are generally sized to store 10 seconds of compressor capacity. So, for example, if you have a 25 horsepower compressor and use a rule of thumb that compressors produce about 4 CFM per horsepower, you're looking at 100 CFM of compressor capacity. If you then multiply by 10 divided by 60 and find out how many CFM you need for 10 seconds, you'll end up with 17 cubic feet, which amounts to a 130-gallon tank. But evening out airflow is not the only thing that receivers tanks do. They also serve as important water collectors. Remember from episode 1 that when pressurized, the dew point of air rises significantly. So condensation is going to form when compressed air cools down. Now, a lot of this is taken out by air dryers, but receivers also collect condensation to protect end-use equipment. However, you have to make sure that your receivers don't overfill with water by emptying them regularly. Receiver tanks can collect up to 1,200 gallons of water per year. This means that a standard 55-gallon drum will need to be emptied about 20 times a year. I once had a case where there was a pressure gauge halfway up a surge tank, and I wanted to replace that gauge with a pressure sensor for data logging. So we undid the screw that held the pressure gauge in place, and water started pouring out. It turned out that the entire tank was filled with water. We had to wait for all the water to empty out of the bottom before we could start using it again. Here's a funny little picture of a surge tank saying, "Do not close the drain valve." This facility is more worried about their tank filling up with water than they are about losing compressed air through the open valve. Ideally, you'd like to be able to control when your receiver tank drains by periodically opening the valve and closing it afterwards. This brings us to the idea of a smart draining valve. Here you can see a device on the bottom of a surge tank that monitors the tank's pressure. When the pressure passes a certain programmed threshold, indicating that there is too much water in the tank, the smart device will open the drain valve and empty the water out. When the pressure gets low enough, the drain valve will close. Smart draining devices with data logging can tell you how often your tank is draining and give you an indication of how much water you're discharging from your compressed air system. This helps you see how well your air dryers are working and if your compressed air system is operating properly. Smart draining systems are inexpensive and easy to install, so you should recommend them to facilities even with a small number of receiver tanks. Smart devices like this are part of a group of devices that we refer to as the Internet of Things, or Industry 4.0, especially when they connect to the cloud, and are exciting developments that allow data to be uploaded directly for analysis. Compressed air is a great opportunity for the implementation of smart devices. You can try simple setups such as the receiver tank example that we just talked about, or if you have more money, you can implement more complex smart projects. Here's a case from the Dubai Aluminum Company Limited. They've done a very nice job improving their compressed air system. They were able to achieve 13% overall savings in their electrical consumption. They did it by connecting wireless transmitters to flow meters that they already had installed in their system. They installed 20 of these wireless transmitters, which then organized themselves in a network. And because the sensors themselves were already in place, they were able to install wireless communication parts on top of the sensors without much impact. It only took about 15 to 20 minutes to install each individual communication node. Now, the sensors cost about $1,000 per unit, and if you have to add flow meters, it will add another half to that amount. So we're really looking at about $35,000 to $40,000 for the entire project. Clearly, only big plants will be able to implement projects like this. Let's look forward to the future of compressed air for a bit. First, even though compressed air can be easily replaced with electric motors, I don't think it's going to go away anytime soon. Compressed air hand tools are lighter, the actuators are smaller, and they work smoothly in terms of how they apply power. They give you precise control over speed and torque, and with compressed air you don't have to deal with the hazards that electrical tools have. I also think that in the future we're going to see more of these smart systems being adopted rapidly. Before long, I am hopeful that small and inexpensive flow meters become available and reduce the cost of projects like to buy aluminum by an order of magnitude. 5 years from now, I think we'll be there. No matter what happens in the future, there are two unchanging factors which will keep us busy with energy efficiency in compressed air systems. First, there are the laws of physics. High pressure air is always going to try and find a leak. And second is human nature. We get busy, we're not paying attention to our compressed air lines, and issues get overlooked. So the last message here is that with compressed air systems, it's almost always about continuous improvement. Thanks so much for your attention during episode 2 of IAC 101. In our next episode, we're going to be taking a look at energy efficiency in industrial cooling systems. Industrial cooling is probably one of the most mysterious areas of industrial energy efficiency, so get excited. Thanks again.